So that should be your supplement 2 there.
Now, after that exam, we need it.
All right, so a lot of times what we do is when we come out of our other circuits and stuff, they don't have enough current to supply our loads. In this particular case, an LED. So again, you know, we can take a very small amount of current going into our base, and then get large amounts of current going through our collector, through our emitter, and stuff like that. So this is one type of application where we can use it for driving an LED coming out of a low, what we would call a low output impedance of a device, and then it's going into a very high output impedance, meaning that it can't drive a lot of current, and then it's going into another high input impedance of our transistor, meaning that it doesn't have much of a loading effect on our output of our other device. And then you can remember that transistors are current-driven devices and stuff like that. And so whatever we have on our base will determine our current going through our collector to emitter. So again, just like any other time, you know, when we're analyzing it, you know, we got our voltage of our base is plus 15 volts, our VCC is plus 15 volts, our RB is 12 kilo, and RC is 1.2. No. So what type of transistor do I have on here? An NPN or a PNP?
NPN.
NPN. So that's our typical one that we use. Just remember, if you're using a PNP, you just have to flip the polarity drop. So on an NPN, you just have to be more positive on your base. On a PNP, you'd have to be more negative on your base. Otherwise, you get treated the same way. So like the same thing, you know, we have to bias our base to our emitter first. That's our first step. So we always kind of circle our active component. So we identify that, put the polarity across our active component from our base to emitter. Treat it as an open, just like we did the diodes. And what would I add for a soft voltage on my base?
Plus 15.
Yeah, plus 15 volts. We got plus 15 volts on here. And then my emitter is going to have, obviously since it's tied right to ground, it's going to be at our 0 volts, so we're going to be biasing our base to emitter. So would that be a go or no go from our base to emitter? Be a goal. Yep, it's going to be a goal, and it's going to do what then? If it turns out to be a goal, it's going to do what?
That's 0.7 volts.
Drop its 0.7 volts. So our base to emitter is going to drop our 0.7 volts. Then what's going to be the remainder then across our RB? Our base resistor. Yeah, 14.3 volts. So our voltage from, for on our chart there then, our voltage from our base to emitter is going to be 0.7 volts. And that's actually a test point. It's from our base to emitter, that's actually a test point, so that one actually would be a positive 0.7 volts. Then our voltage from our base, referencing it to ground. Again, another test point, and that would obviously be the same thing as B to E, so that would be also another positive 0.7 volts. Then our voltage across our B then, we said is going to drop the remainder amount of voltage, and then that's going to be your 14.3 volts. Then what's my current going through my base then?
That's mine. Did you bring it over?
Yeah, no, but so remember our current is divided depending on our resistor, right? So keep so it's going to be 14.3 divided by 12K.
What?
Bring the truck over here.
So 1.19 milliamps.
Yeah, so it should be 1.192 milliamps is what you really should actually get. You know, for there. All right, so 1.192 milliamps. And then what's my what would be my next step after that then? So we know that this LED, or the base emitter, I should say, takes its voltage first, and then we have another solid state device up here, and that's always going to take its voltage first too. So you can also identify that active element. And LEDs, a typical LED is, for approximations, we can use 2 volts. So it's always going to be given its 2 volts first. And then the current is going to depend on one or two things. It's going to be dependent on, so remember that IC is equal to what? What is IC equal to if I'm using a transistor? Yeah, your beta DC times your IB. Okay? That's going to determine how hard they're driving that transistor. So what's my calculated current for IC? If I don't give you beta DC, what do we use for approximations? 200. So you're just going to take your 200 multiplied by your IB, and what do I get for IC? Yeah, so you're going to get 238.4 milliamps. That's going to be our current going through both our collector and emitter, because remember our current going through our emitter is approximately equal to IC, so that's going to be also the same current going through IE. So once we know two things about our component, then we can always find the third. So what's my voltage going to be across RC? Yeah, what did you get for a big number? Yeah, so you end up calculating out 286.1 volts. Well, we know that's not true. Remember from the lecture from the last time, if we end up getting a large voltage across our collector that's more than our source voltage, what's that telling us about our... Yeah, we're in saturation. And we know that we can't get any more voltage than what our VCC is. So if we're in saturation, then what's my voltage drop going to be across C to E then?
0.
Approximately 0, but otherwise we use approximately 0.22 volts. So remember, if we're in saturation, our this thing is acting like a switch. It's actually closed as far as it can, and that gives us an approximation of 0.2 volts going across our collector to emitter. So once we identify that our collector to emitter is actually really in saturation, it's just like a closed switch, that's going to take its 0.2 volts. We know that this LED is going to take its 2 volts. So how much is going to be the remainder going across RC? Yeah, so it's going to be, so it's going to cross out, and we're going to go with 12.8 volts. Okay? Because we know that, because we really want to treat these transistors as switches, so we really want to either fully turn that transistor on or fully turn it off. So we're fully turning that transistor on. The collector to the emitter voltage is dropping down to 0.2 volts. It's going to take its voltage first. The diode is going to take its voltage first, or is also going to take its voltage, and then the remainder is going to be dropping across RC. And then that gives us 12.8 volts. Now what is our current going through our collector? Yeah, 10.67 milliamps. So that'll be our, so that's going to be our new current going through our collector and our emitter, and also through the LED. If I were to have a VCC of 300 volts in there, it would literally drop that 286.1 volts across that RC. But since we don't have a voltage source that large on here, we only have it 15 volts. The transistor is still going to be in saturation, and it's going to take its voltage first, and then the LED is going to drop its voltage, and then the remainder amount from the source voltage is going to be dropped. And then that gives us our 12.8 volts across RC with our 10.67 milliamps of current going through it. And so that's how much current will be going through the LED. Let's see, then, so we have...
So the IC is going to be 238.4, or is it going to change?
Yep, that's going to change. Yep, that's going to change to those two numbers right there. Yep. Once we get into saturation, so we have to make sure that we really exceed. We really want to drive that transistor really hard to make sure that it's fully turned on and that we're not getting the voltage drop across our CD, other than the 0.2 volts when we're in saturation. That's the other thing. So when we're calculating these things out, we still just calculate them out to make sure that we are truly indeed getting a lot more gain than what we're really capable of on our for our collector voltage there to maintain that saturation there. So we really want to drive that transistor really hard to get that LED to fully turn on. Or if I remove the base and I tied it to ground, that it would fully turn off, and then it turn off that LED. So if I put a voltage on my base, starts driving the transistor, biases the base to emitter, acts like a switch, it closes, and then the current is going to start flowing through our collector to emitter.
You said the current through the LED is also
Yep. Yep. As you can remember, we can kind of treat these as two separate circuits. Here's my collector to the emitter. That's one circuit, and then the other one is base to the emitter. Yep, and then so they're just in series. Okay. And so the LED would be turned on.
And then we still assume BC is 200.
No, yeah.
Or I mean BC, the
CD would be, then your voltage across CD would be 100 millivolts. Okay? So our current is still determined by this, but we can only still drive our total collector current based on whatever our source voltage is on that. Okay? So that's one application of an LED for an LED driver.
Well, what's the voltage? This is voltage DC.
Yeah, so volts, so again, volts DC then.
No, DC, voltage.
Yeah, volts VC. Yep.
Just C. Yeah.
Yeah, VC, yep. So my red lead's on C, my black lead's on ground. It's a test point. So what would I measure for voltage? 0.2 volts. Positive 0.2 volts. Yep. So if I wanted to change the current going through that LED, if I wanted to change that current going through the LED, let's say I wanted to get, maybe it's not as bright as I wanted it to be, I could go ahead and lower my RC a little bit. It's still going to drop to 12.8 volts as long as I recalculate it out that I'm more than my PCC. So if I drop my RC, then my current going through my LED would also increase. But I always have to make sure that I'm always maintaining that I'm in saturation. Which in that case I could go ahead and lower that RC, and that would determine my current going through RC. Not really, actually we're just kind of treating it as two different circuits. Yep, our base to emitter, that's one circuit. Then our IC to IE.
So the Q1 in saturation would be closed then?
What's that?
Q1 would be closed?
Yep, Q1 would be closed. That would be just like a switch. It would be just like a switch. Boom. So if I, yep, on or off. Yep. So if I were to, for a particular application like this, since we're using them as a switch, it'd be the same as me drawing in a switch right from my collector to the emitter. Bam, I close my switch. The current starts to flow. My current is going to be dependent on whatever RC is. So whatever, so if I change my load on here, my current's also going to change. If I remove my base, then that switch opens up, and then all my collector current and my emitter current is going to come to a complete halt, and then the LED will turn off. Yep, so you just kind of treat it as a switch. But I'm kind of stressing out here that, depending on what this load is, if I change my RC, I'm going to change my current on this particular circuit. Okay, so I'm kind of stressing that out. We're going to see a slightly different application on our next sheet there. So if my load changes, my current's going to change along with it.
So your IE current will be your IC current?
Yep. Remember, typically IE is equal to IB plus IC, but IB is such a small amount of current typically that it's negligible, we don't have to worry about it, so we just say that IE, for all approximations, that IE is equal to IC. Yep. Alright.
And the
LED would be on.
And the LED would be 2.2.
What's that?
The LED would be 2.2.
The LED would be 2 volts. Yep, the LED itself, the light emitting diode, is going to be 2 volts.
So if you don't treat it as a light.
Nope, not an LED. An LED is going to drop 2 volts. Yep, a diode would drop, a diode would drop 0.7 volts. An LED would drop 2 volts. If it was a zener, it would drop whatever the zener voltage is. Yep. So depending on what type of solid state device it is going to determine what that voltage is across
Well, I
there.
just look at, if you put your black on ground and put your red on LED, it'd be 2.6.
If I go up here, if I go from here down, then I would get a positive 2 volts plus a positive 0.2 volts. I'd get 2.2 volts.
So you're just measuring across the LED.
Yep, measure across the LED and across my collector to emitter, because there is a slight voltage drop across my collector to emitter. So it'd be 2.2 volts.
2.2, okay.
Yep.
So the answer to BLED is 2.2.
Oh, VLD. Oh, VLD. If I'm just measuring the voltage across the LED, then it's just the 2 volts. Yep. But if I'm referencing it to ground, then I would be 2.2 volts. But yeah, the voltage across the LED is just 2 volts. Yep. Yep. So this is probably one of the more practical applications that you're going to use in a simple method. Yeah. Well,
So IE is always going to be equal to IC in the circuit?
yes. For approximations. Realistically, IE is actually going to equal to IV plus IC. Because we have this current that's going up through here, and then we also have this current going up through here. But typically, the current going through RB is so much smaller than the current going through IC and IE that it's negligible. We don't have to worry about it. Not for approximations. Yeah. But we do have both those two currents, because some of my current's going to split. It's going to come up, some of it's going to go through RB, and then the majority of the current is going to go up through IE and then up to IC. Yeah.
So what would BC?
So BC. Yep, so it's just I just took my red lead and put my black lead on ground and my red lead up here from C to E, then I would measure my positive 2 volts.
0.2?
Or I'm sorry, positive 0.2 volts. Yep.
That doesn't do anything with the diode.
Nope, not since we're from here to here. So CDE is just only measuring that voltage drop across CDE. Yeah. So if we don't know what beta is, use 200, calculate it out. If we get more voltage across RC than what our source voltage is, then we know that we have to recalculate it out and then determine the new current. But then at least we know then for sure that we're truly in saturation. If we recalculated that out, then we know that we're truly saturated on our collector to emitter. So that's kind of the big thing, just making sure that we're going to use it as a driver. We just have to make sure that we're in total saturation. All right, that makes sense. Everyone good with that? Yeah, very. What's that?
I don't know. Question. I'm sure I'll get it answered at some point here.
You want me to run through it one more time?
When you add in the current of it, isn't a pretty round number, is it right now for the circuit?
Say that one more time.
The current for the total current isn't a pretty small number, is it?
This current here,
Is that the total current there?
that's the total current.
Alright.
Yep, and that will be the actual current of it.
Can you help us fill in the bottom part? I want to make sure I got it right, or in order.
Yep, okay, so which one,
Just go down the list.
oh, okay. All right, so VDE, so my voltage from VDE, so that's a test point. Got my red lead on B, my black lead is on E,
Okay.
and what would I measure for voltage?
Positive 0.7.
So a positive 0.7 volts.
Okay.
It's the voltage drop across B to E. And then the voltage from the base, which is another test point, red lead on my base, my black lead on my ground,
It's going to be the same.
what would I measure?
Same.
Positive 0.7 volts. My voltage across RB, so now I'm just looking at a voltage drop across RB. So what do I have for a voltage drop across RB?
14.3.
14.3 volts. IB then, since we know the voltage across RB and we know the resistance of it, then my current going through RB is going to be 1.192. That's always milliamps, and that's always going to stay the same. Then when we calculated out our IC, we calculated out the first time around, we calculated out that was 238.4 milliamps. So that was our first time that we calculated it out. And then we found out that we had more voltage than we did our VCC. So then we had to recalculate it out. So then we crossed that out, and over in the right-hand side column, then we just went ahead and put in the voltage across RC was our 12.8 volts, and then we recalculated it out to be the 10.67 milliamps. So then the real answer for IC would turn out to be 10.67 milliamps.
And IE, right?
And then the IE would be the same then, for approximations. Otherwise, we really know on this one here, it is actually a noticeable difference, because we really would have IC would really, or IE would really actually equal like 10.67 plus my 1.192 milliamps.
Yeah.
So it would be a noticeable difference on this one, but for approximations, it would still be fine. Just to keep our rules consistent, our rule is kind of IE equals IC. But it would equal, what, 11 point something, it'd be a little bit. What is it? Somebody said 11.8?
Yeah, 11.86.
Yeah, 11.86 is really what the true current going through IE would be. Let's see, so we calculated out IB, IC, IE, we got that. And then the current going through the LED, what would be the current going through the LED then?
Is that going to be that 10.67 milliamps?
The 10.67 milliamps. No matter if it was approximations or not, that would be the true current going through this. Because the other 1.192 milliamps would be going through the basic emitter, so that 10.67 would always be there. Then the voltage of RC, then we talked about that. That was first calculated out 286.1 volts. Found out that was too much. Recalculated it out by subtracting. Once we figured out that was in saturation, we gave the collector to the emitter its voltage of 0.2 volts approximation, and the LED took its 2 volts first, and then the remainder was the 12.8 volts going across to RC. Then the voltage of the LED, that's 2 volts, and that's going to depend on whatever your data sheet is. So if you're driving a whole different type of LED, you can look at your data sheet and find out it might only be 1.5 volts. Then you would use that for your voltage drop across your LED. If you don't know what the voltage is across your LED and you don't have the data sheet, then just use 2 volts for an LED. Then the voltage from the collector. Basically, you got your red lead on your collector, black lead on your reference point or your emitter. Come back down, you're going to have a positive 0.2 volts.
Wouldn't you include the 0.7 volts as well?
Nope, that's a separate circuit. Remember, that's kind of... Yep, those are 2 separate circuits. Yep. We're not going through our base to emitter. Our base is emitter, so we're only going through our collector to emitter. Then CD then would obviously be the same then, a positive 0.2 volts approximation. And yes, the Q1 would be on, or the transistor would be turned on, fully saturated, and the LED would be turned on as well.
So on is both.
if we, so let's just, we'll just do a quick troubleshooting one here. So let's treat it that if I had an open RB, meaning that this resistor burnt out or came unsoldered or something like that, then we'll use the arrow method to do the troubleshooting. So if I have an open RB, meaning my base resistor opens up, what would be my voltage from, what would happen to my voltage from B to E then? So if I have, so I'm looking at, let's see, I'm looking at my voltage from B to E. So if I have my RB is open, I have my red lead here, my black lead here, what's going to happen to my voltage going across from my base to the emitter? It's going to be 0 volts. So that one's going to, so did that one increase, decrease, or stay the same? It decreased because it went from a positive 0.7 volts down to 0. And then how about my voltage of my base? What's going to happen with that then? And that's the same as BDE, so that one, if the other one went down, so did that one. That one's going to go down. Then what's going to happen to my, oh, I should, see, let's, yeah, so now if I, these are where things get kind of a little tricky here. So now what's going to happen to my voltage going across R to B? So what's my voltage across RB now?
It would go up to 15.
Well,
Not really.
not really, exactly. Not really, because if I have 0 volts here, so on my previous one, if I have 0 volts here and 0 volts here, is my base emitter, is that a go or no go?
No go.
No go. So that's another open, right? So my voltage from my base across my base resistor is going to be 0 volts because I still have this open here. I don't have any current going through there. I have another open. So this is kind of like this part here is another open. Okay? So that voltage is going to go down. That's going to go down to 0.
Is it possible that some meter leads may cause forward bias?
Oh yeah, the minute I put my, so if I do have an RB and all of a sudden I go ahead and put my ohmmeter on there, and so I put my voltmeter on there, I'm going to start getting the current going through that base. I'm going to start biasing this transistor, and that LED is going to turn on. Yep. Now this voltmeter is 10 megohms. I might not put it into saturation, so that LED might just turn on a little bit dim. Sometimes we have to look for it. But then remember, I kind of talked about digital circuits and stuff like that. And all of a sudden, I'm doing some troubleshooting. All of a sudden, I put my voltmeter across something. All of a sudden, I can turn that whole circuit on just by putting my voltmeter in there, because that voltmeter has some resistance. So we do have to be careful of that. So when we're troubleshooting it, all of a sudden we can turn on this load. This could be some kind of an actuator or something like that. Our machine could start running again by us doing our troubleshooting. So we do have to be a little careful about when we're sticking in our voltmeters in there. Yeah. So let's see, just out of curiosity, I'm going to just take my 10 megohms. I'm going to take my 14.3.
Right be about 14 microamps.
About 14 microamps?
Yeah.
So 14 microamps times 200. So that gives me 2.8 milliamps. And then I know that I got, so that would be, my collector current would be 2.8 milliamps, because I'm just kind of taking calculating out IB times my beta. So if I got 14 microamps on my base, I'm times them by 200, figuring out what my collector current would be. That would be at 2.8 milliamps. And if I multiply that by my 1.2 k ohm, so I'd be at about 3 volts dropped across there. So I get 3 volts. I get 3 volts dropping across here. I get 2 volts getting dropped across my LED, and then the remainder amount of voltage would be getting dropped across CDE. So it wouldn't be in saturation, but it would be
Enough to flicker it
enough
off.
to get the light to dim. Yep. So that light would dim just slightly. All right, then if we, so that was voltage across our RB. Then what would happen to my current in my base then? So if I get rid of my old voltmeter here again. So then what's my current going through IB without the ohmmeter or voltmeter in there? And I got an open RB. What would happen to my current going through RB? It'd go down, it'd go to 0, right? It's an open, so there's no current going through there. So IB would drop down to 0. And then what's going to happen to my current going through my emitter? 0. So that would go down. My current going through my collector would be what? 0. Yep, that would also be 0. So if IE is 0, then IC is most likely 0. So that one would go down. Then the current going through my LED, what would happen to that?
Go down to 0.
Go down to 0. And then my voltage across RC would, what would happen to my voltage across RC then? What's that?
Go up.
It would go down. There's no current going through, if I don't have any current going through RC, if I take my 0 times 1.2 kilo ohms, that'd give me 0 volts going across it. So where's all my voltage going across then? C to E. Yeah. The transistor's wide open. That's the open. So then the voltage across the LED is going to be what? 0, because the CDE is taking all the voltage. Then my voltage from my collector is going to be what? So if I measure right here, what would I measure for voltage?
Source voltage.
Source voltage. So that one would go up. And then CDE is the same thing that we just measured, and that one also would go up. And then would Q1, would that be on or off? Off. And then would the LED be on or off? Off. Okay. Yeah, we got to be a little careful when we're doing our troubleshooting, and then just kind of remember, you know, what's open and what's not. You know, so the only way we can have these ones closed is if we have current going through there. If there's no current going through there, then we just treat those as an open. For example, the BDE and stuff like that. Okay. All right. Any other questions on that one?
Doesn't your LED act like an open if there's no current through it? Why would your CDE drop your source voltage?
Yeah, you know, that's got to be the same kind of situation. That could be kind of a, yeah, that would be probably a questionable one too. Yeah. Yep, you would be, that one would be kind of questionable. Here I would measure my source voltage. Yeah, you're right. Yep, because I forgot about that LED, because that would be the same situation as this here.
Right.
Yep. So definitely from here to here we would get
Source voltage.
source voltage. From here to here it would be very questionable.
Yeah.
Yeah. The only way that would be questionable would be because all of a sudden again, you know, if I did end up putting in a voltmeter in there, now I'm putting a 10 mega ohms, now I can turn on that LED and boom. Ideally we could say 0 though. Yeah. Yeah, you're right. Ideally from CD would be actually 0. But when I put a voltmeter in there, then who knows what's going to happen.
So will that increase or decrease the temperature of those answers?
theoretically it would say decrease down to 0, yeah. So CDE theoretically would be 0. But I would put a little question mark on there, you know, with a little note saying, what about my voltmeter? Theoretically 0. Practical, you probably would end up measuring some voltage. Yeah.
I recounted my test and I got 28, not 27. And it was great.
Okay, let me, we'll take a look at it
Mine was
here
off
after.
a little bit too.
Yours is off too?
Yeah.
Is everyone's off by 1?
I was off by 2.
Really?
Did you?
I'll take a look. I'll take a look. Yeah. Hit me up afterwards and we'll take a look at it.
Okay.
Yep. Maybe I copied your scores down wrong.
Did you have that eye clicker?
Yeah, it would be on the eye clicker part. That's the part that you got, that you found the error, right, on the eye clicker? Okay. Yeah, let me know. And I'll take a look at it and I'll go over them all. All right. Any more questions on that one? Is that pretty okay on that one then? All right. All right, let's take a... Now remember on this one here too, I was kind of stressing out too that if I change my RC or change my load, you know, this is kind of my load. These two components here becomes my load. If I decrease my RC, then my current's going to go up. If I change any of that part of my load on this particular circuit here, if I change that resistance of that load, my current is going to change with it. Okay? All right, let's take a look at the next one here. A little bit different configuration. All right, so then again, we just kind of analyze it the same way. Circle my active component, put my polarities in there. Bring your soft voltages over. So we know we have a VBB or a VB of plus 5 volts. And our VCC is going to be plus 15 volts. So what's my soft voltage on my base? Treating this as an open, what would be my soft voltage at this point here?
Plus 5.
Plus 5 volts. Okay, then on my emitter side, what did I get for a soft voltage on my emitter side? 0 volts. So plus or minus 0 volts. That would be a goal, and that's going to do what? It's going to drop it to 0.7 volts. So the current going through the LED is going to be this way, going from our negative to positive, so that's our current going through our, put it that way. So our current going through our basic emitter is going through that way. We know we got current going through there, so my polarity across RE is going to be that way. So then once we determine that basic emitter turns on, it's going to drop it 0.7 volts. What's my voltage across RE going to drop? 4.3 volts. Okay, because we know that when I bring my red lead over to my black lead, I need to make sure that I equal out my source voltage. So as I come through, bring my red lead around, a positive, negative. My first voltage that I see is going to be a positive 0.7 volts, and then the remainder must equal so I get my source voltage. Then I'm going to get a positive 4.3 volts. So whichever circuit way I go, I need to make sure I end up with my positive 5 volts. So that means that RE is going to drop my 4.3 volts. We know that RE is equal to my 330 ohms. So what's my current then for 13.03? 03 milliamps. Okay, so that's going to be my current going through my emitter. Now, I've already determined that I have 13.03 milliamps current going through my emitter. So what's that going to be for current going through my collector? Yeah, or I can just say, since my LED's on my collector, what's my current going through my LED? Yep, it's going to be the same, because IE is equal to IC, so then we know that my current is going to be the same going through there. I know that my LED, if it's not given, we're going to say is going to drop our 2 volts. So now once we determine, now we have all but our collector to emitter, that's the only voltage that we don't have determined yet. But we know that the LED is already going to, we already know that the LED is going to have current going through it, as long as our polarity is correct on our LED, and we do. We know that we're going to have that 13.03 milliamps current going through there, and it's going to drop its 2 volts. RE is going to drop its 4.3 volts. So how much voltage then is going to be dropped across CDE? Well, so take your 2 volts plus your 4.3 volts, so you give us 6.3 volts. Subtract it from our 15 volts, and the remainder is going to drop across our collector to the emitter. Okay? So, yeah, you'll end up getting, going from CDE then, you're going to get your 8.7 volts. Okay? Now the LED is still turned on. We're not in saturation, right? Because we're not measuring our source, and we're not measuring our 0.2 volts going across our collector emitter. But yet the LED is being turned on in this particular case. Okay? The current is being controlled by RE. We're going to make sure that we have 13.03 milliamps of current going through there. And then CDE then, since this is RE's already determined what the current is going through there, my transistor is automatically going to adjust itself to make sure that it maintains 13.03 milliamps going through my collector. Okay? So that resistance, this time it's kind of more of a variable resistance. This time now what this circuit looks like. The other one actually looks like a closed switch. This one here is going to act like a rheostat. And that transistor in between the collector and the emitter is automatically going to adjust itself so that it means 13.03 milliamps both through the emitter and the collector. And that resistance, internal resistance of that transistor is automatically going to adjust itself so that it regulates that current. Okay, so now this time we have more of a current regulator. All right, so our LED is going to drop its 2 volts. It's going to have 13.03 milliamps going through the LED. My voltage of my, so what's my voltage of my collector on this particular one? So here's my DC. So what would I measure for voltage then from DC? How much?
13 volts.
Yeah, 13 volts then. So you'd end up getting your 13 volts from DC. Because it would be, if we were to actually put in our current paths, We know my current's coming up, negative, positive, negative, positive, negative, positive. So I'm just taking my 8.7 volts that my collector to the emitter is dropping, of my 8.7 volts, plus my 4.3 volts, and I get my positive 13 volts then going from my voltage of my collector. Then is that, and we already did determine that the LED is turned on. We have enough current going through it. We have enough voltage across the LED, so the LED is turned on.